What if I told you there's copper on Earth that refuses to rust, and it's been sitting in plain air for thousands of years? No vacuum, no climate control, no modern coatings. Just time, oxygen, rain, and history doing what they always do, except somehow not doing it here. So the uncomfortable question is, did ancient metallurgists stumble onto a secret alloy we still don't fully understand? You already know copper. It turns brown, then green. Statues get that familiar skin of corrosion called patina. Pipes scale up. Coins darken in your pocket. Copper is famous for reacting with the world. And yet archaeologists have found copper artifacts that seem almost stubborn. A knife here, a vessel there, a tool pulled from soil that should have eaten it alive, still intact, sometimes even sharp-edged. Not pristine like it just left a factory, but preserved in a way that feels out of proportion to its age. Then there's that pillar in Delhi. You can stand in the open air and look up at a 7-meter iron column that dates to around the 4th or 5th century. It's not copper, it's iron, but it does something copper is supposed to do better. It resists corrosion in a way that looks like cheating. It's one of those objects that makes you wonder if ancient metalworkers were just different. Different methods, different ores, different rules. So you start looking at copper again with fresh suspicion. Because some ancient copper is just copper. It's copper the way bread is bread, technically true, but missing the recipe. Early metallurgists worked with native copper, then smelted copper from ores, and the ores were never pure. They carried companions: arsenic, antimony, nickel, silver, lead, iron, sulfur. Sometimes those impurities made the metal worse. Sometimes they made it better. Sometimes, without anyone planning it, they created an accidental alloy. And accidental alloys can behave like secrets. Take arsenical copper. Before tin bronze became widespread, many cultures used copper naturally contaminated with arsenic. It can make copper harder, sometimes more workable, and it can change how corrosion starts. That doesn't mean it becomes rust-proof, but it can change the pace of decay. It's the first clue: composition matters more than the name stamped on the museum label. Now add the environment. Corrosion isn't just metal plus oxygen. It's chemistry plus humidity plus salts plus acids plus microbes. Under the right conditions, corrosion products can form a tight, protective layer that slows further damage. On copper, that protective layer can be oxides, carbonates, sulfates, compounds that can act like armor. You've seen the green on old roofs and statues. That green can be destructive in some cases, but in many cases it's protective. It's copper's version of a scar that seals the wound. So when you hear, "it didn't corrode," sometimes it means it corroded into a stable shell and then stopped. But the mystery doesn't die there, because not all patinas are equal. In coastal air, chloride salts can trigger bronze disease, a nasty cycle where corrosion keeps feeding itself. In polluted urban air, sulfur compounds can form different crusts. In dry climates, corrosion can crawl. In wet, acidic soils, it can sprint. Two identical objects can age like completely different species depending on where they sit. And ancient objects didn't sit politely in a lab drawer. They were buried, burned, lost in rivers, stored in temples with incense smoke, dropped into shipwrecks. Each one lived inside its own chemical story. Still, you keep noticing something. Certain ancient copper and bronze artifacts survive astonishingly well, even when the conditions seem unfriendly. Sometimes the surfaces show unusually uniform, glassy-looking layers. Sometimes cross-sections reveal a dense corrosion front that looks organized. Then the speculation starts to creep in. If you were an ancient craftsperson and you noticed that copper from one mine lasts while copper from another rots, you'd learn fast. You wouldn't need a periodic table. You'd need memory, tradition, and a reputation to protect. You'd choose certain ores. You'd recycle certain scraps. You'd add certain fluxes. You'd quench, hammer, anneal, and watch what happens over decades. And if that knowledge worked, it would sound like magic to anyone who didn't inherit it. Now widen the lens. Ancient metallurgy wasn't primitive. It was empirical science done with fire and patience. Smelting temperatures, furnace atmospheres, slag control, charcoal quality, crucible materials, tiny variations could change the final metal. Even the microstructure matters. Cast copper can trap impurities differently than worked copper. Repeated hammering and annealing can change grain structure and distribute inclusions. Those inclusions can either become corrosion weak points or help form protective layers, depending on what they are. It starts feeling like you're tracking a lost recipe. Not one secret alloy, but a web of half-secrets. Local ores, controlled impurities, and craft choices that nudge corrosion down a safer path. And there's another reason this feels convincing. Modern engineers do the same thing. We intentionally alloy metals to resist corrosion. We design weathering steel that forms stable rust. We create stainless steel by adding chromium so it forms a passive oxide film. The whole trick is to let the surface react, then lock it into a protective state. So you start wondering, did ancient metallurgists accidentally invent their own version of passivation for copper? A copper that forms a barrier so tight the world can't get through. If that happened, it wouldn't require a conspiracy. It would require time, selective tradition, and a few lucky minds. By now, qualified people have asked similar questions, just in less dramatic language. Archaeometallurgy is a real field. Researchers analyze ancient metals with techniques like X-ray fluorescence and electron microscopy to map elements and corrosion layers. They compare artifacts from different sites. They study slag to infer smelting conditions. They trace lead isotopes to identify ore sources. This isn't guesswork. It's forensic science on history. When scholars examine unusually well-preserved copper alloys, they often find patterns. Tin bronze forming stable tin-rich oxides, arsenical copper with different corrosion behavior, trace elements like phosphorus sometimes affecting hardness and oxidation, and protective mineral layers formed by burial chemistry. Conservators in museums also know a harsh truth. Sometimes an object only looks uncorroded because the corrosion is doing its job quietly. The surface may be a stable layer that hides how much metal has been transformed underneath. Other times, cleaning in the past removed active corrosion and left a calm surface behind, giving you the illusion of miraculous survival. And that iron pillar in Delhi? Scientists have studied it for decades. One key idea is that its corrosion resistance comes from a protective film rich in iron hydrogen phosphate hydrate, aided by the pillar's composition, particularly higher phosphorus content than many modern irons, and the way it was forged. Even then, it's not immortal. It shows corrosion where conditions change, like near the base. So here comes the twist. The secret alloy explanation is usually not what mainstream science needs. Most experts don't think ancient people had a single lost supercopper formula. They think you're seeing a combination of ordinary processes that look extraordinary when you compress time into a museum display. Copper doesn't rust like iron. It oxidizes, and its corrosion products can be relatively stable. Bronze, especially, can develop layered corrosion where tin concentrates near the surface, creating a more protective barrier. Burial conditions can mineralize an artifact in a way that preserves its shape like a fossil, even if much of the original metal has changed. And the cases that sound like couldn't rust often soften under close inspection. The artifact did corrode. It just corroded into something that protected it, or it corroded very slowly because the environment was unusually dry, alkaline, or lacking in chlorides, or because it was sealed away for most of its life and only recently exposed. In other words, the mystery might be less lost technology and more misleading intuition. You expect time to destroy everything evenly. Nature doesn't work that way. Nature picks favorites. But the story doesn't resolve cleanly either. Because even if mainstream explanations cover the big picture, they don't make every specific case feel satisfying. Corrosion science is messy. Tiny differences in soil chemistry can flip the outcome. Microbes can accelerate or inhibit corrosion in ways that are still being mapped. Two objects from the same site can age differently because one sat near a piece of wood, or a bone, or a pocket of salts. And ancient production really did vary, not just in recipe, but in method. Furnace atmospheres could be more reducing or more oxidizing. Slag could trap certain impurities or release them. Recycled metal could accumulate trace elements over generations. An alloy could drift without anyone naming it. So maybe there wasn't one secret alloy. Maybe there were many small secrets, practical heuristics that created metals with unusually stable surfaces. Secrets that weren't written down as chemistry but lived as craft, which ores to trust, which scraps to mix, when the flame color looks right, when the metal sounds right under the hammer. And here's the uncomfortable middle ground. Science can explain the mechanisms, but it can't always reconstruct the exact chain of decisions that produced a particular artifact. The physics is universal. The history is not. When you stare at a piece of ancient copper that seems to have outlasted its era, you're not just seeing metal. You're seeing a collaboration between human hands and the local earth. A specific mountain's ore, a specific forest's charcoal, a specific workshop's air, a specific burial's soil. 1,000 tiny factors that never repeat in the same way again. So did ancient metallurgists have a secret alloy? Maybe they had something better than a single formula. Maybe they had a relationship with materials, patient, observant, generational, that let them ride right along the edge of chemistry without naming it. And maybe the rust-proof copper isn't a miracle at all, but a reminder that what survives isn't always what was strongest. It's what found the perfect way to make peace with time. Because in the end, the strangest thing about corrosion isn't that metal decays. It's that sometimes, decay is exactly what keeps it alive.